Okay, so this is the last of the conic sections. Hyperbola. So hyperbola, if you look at the definition of the ellipse and of a hyperbola, they're the same except for one word, right? What is the word? Difference, right? For the ellipse, it was the set of all points, the sum of whose distances from two fixed points is constant. For hyperbola, it's the difference, right? So if the hyperbola has two branches. Each one kind of looks like a parabola. It's not. I mean, if you had a hyperbolic satellite dish, it would not reflect everything. All parallel rays would not reflect to the focus. So it's not a parabola, but they kind of look like parabolas. Every point on a hyperbola, if you took the distance from that point to one focus and that point to another focus and subtracted, you're going to trace out these two branches. And the reason that there's two is because it matters the order of the subtraction, right? If actually the D1 is bigger than D2 and you take the absolute value, you're still going to get the same value, right? The absolute value will turn it positive. So the absolute value is why. The order of subtraction, one of them will get you that and one of them will get you that. So there's two branches. Each one has a focus which is inside, kind of like a parabola. Each one has a vertex right where you expect to see a vertex on a parabola. And, you know, HK still means the center, like it did with an ellipse. A is the distance from the center to the vertex, just like it was in an ellipse. And C is the distance from the center to the focus, just like it was in an ellipse. You know, what's the difference between an ellipse and a hyperbola? They've reversed their position, right? Now, for an ellipse, the focus was inside the shape, so C was always less than A. That's not the case anymore. Actually, C is bigger than A. Always C will be bigger than A. Okay. And if you look at these here, since for every point on these shapes, the difference is constant, then it has to be the same even for the vertex, right? Even for the vertex. So if we were going to do the subtraction from this point to this point minus this point to this point, right? Well, you can see that from the vertex to the opposite focus, it's going to be the length of from vertex to vertex, which is an A plus an A. And then it's got this little piece right there, right? But when I subtract the distance from that vertex to that focus, that's the same little piece. So what do we get when we subtract? 2A. Right? This difference, whatever this difference is, it's 2A. So if it works that way for the vertices, it's got to work that way for every point on there. So 2A for every one of these points, the subtraction is 2 times A, where A is the distance from the center to the vertex. And what else is different about this? Now we use the word transverse axis, where in an ellipse we call it a major axis. Now we're calling it a transverse axis. A little bit of a vocabulary word. So we have two standard equations, depending on whether or not it's horizontal transverse axis or vertical transverse axis. And looking at the equations, they look pretty much like the ellipse, except for one difference. You just compare the horizontal one. What's the only difference between that equation and the standard equation for a horizontal ellipse? It's a minus, right? Which makes sense because we changed the sum to a difference, so that's where it's different. Now, here's what else is different. Okay, notice what changes when you go from a horizontal to a vertical. In an ellipse, it was where you found the A squared, right? A squared, the bigger denominator, was always, that could be underneath either one. If it was underneath the X, that meant it was a major axis horizontal. If it was underneath the Y, that meant it was major axis vertical. But what's changing here? It's not the A squared and the B squared. They stay the same no matter what, right? They stay the same. What's changing? Is the first term the X term or is it the Y term, right? So for a horizontal, it's the X term, which is first. For a vertical, it's the Y term that's first. And because it's a subtraction, and it's not okay to write them in a different order, right? If it's horizontal, the first term is positive, and it's the X term. If it's vertical, the first term is positive, and it's the Y term. So you know which way it goes by whatever is the sign of the variable that has the positive term. Okay, now if you look at the graph, we already did this on the last slide, but you know the distance from the center to the vertex is definitely less than the distance from the center to the vertex, to the focus, which means our Pythagorean theorem kind of relationship is not going to hold, because for an ellipse, A was bigger than B and C, so A squared equals B squared plus C squared. For a hyperbola, actually, it's exactly like the Pythagorean theorem. C squared equals A squared plus B squared. C is the bigger of all three. So the relationship, and I don't think it shows up here, is C squared equals A squared plus B squared. And from this, you could tell what the A is and you can tell what the C is, but you can't yet see what the B is. But it takes us a couple slides to get into where's the B come from. But it'll come up in a couple slides. Okay. So find the standard equation of a hyperbola. If it has foci at negative 1, 2, and 5, 2, and vertices at 0, 2, and 4, 2. Okay. So again, it did not actually ask you to graph, but I'm going to sketch a little bit just to help me understand if it's horizontal or vertical, which equation to use, what values do I already know, which ones do I need to figure out. So let's see, negative 1, 2, and 5, 2. So I should draw this in like this. Negative 1, 2, and 5, 2. 1, 2, 3, 4, 5. Right, those are the foci. And vertices at 0, 2, and 4, 2. So which is this, horizontal or vertical? It's got to be horizontal, right? Because you could see that the transverse axis is horizontal. So we know that if that's the vertex of one branch, the branch kind of opens up around like that. Okay, so if it's horizontal, we want to use this one. X minus H squared over A squared minus Y minus K squared over B squared equals 1. So we need to know this. We have to be able to fill in for the center, HK, A, and B. And we definitely could figure out the center. What is the center? Yeah, I mean, halfway in between the vertices or the foci would be 2, 2. Right there. There's your HK, which is 2, 2. And the A is the distance from the center to the vertex, which is 2. Looks like A equals 2. And what is C? C is the distance from the foci to the center. C equals 3. Okay, but we need to know B. So how are we going to find B? It's going to use Pythagorean theorem, twin, right? C squared equals A squared plus B squared. So the C squared will be 9. These numbers always, they keep repeating themselves over and over again here. Equals 4 plus B squared. So B squared equals 5. And actually, we don't need b, we need b squared. So we've got everything we need to plug into that equation now. Right? That equation will be x minus 2 squared over a was 2, 4, minus y minus 2 squared over 5 equals 1. Okay, Courtney. So now use asymptotes to sketch a hyperbola. Example 2. So now we're going to see where the b comes up, and it involves asymptotes because hyperbolas have asymptotes. So first, is this equation in standard form? Because why? Because it doesn't equal 1. So we have to do the same thing we do with ellipses. In order to put it in standard form, we're going to divide by 16, right? So here's this in standard form is x squared over 4 minus y squared over 16 equals 1. Okay, so is this horizontal or vertical? Because the first term is positive, and it's the x term, horizontal, right? So this is horizontal. What is the center? So you see, you don't see anything being subtracted from x and y, so the center is 0, 0. What is A and what is B? Remember that now A can be less than B. In this case, it is. The A is always under the first term. In this case, that's A squared. So A equals 2. This is the B squared, and B equals 4. In fact, A can equal B. Right? That can't happen. A can't be equal B in an ellipse, or else we wouldn't have an ellipse. It would be a circle. But on this, A can be bigger than B, less than B, equal to B. We don't have anything that we can count on like that. So let's see. So this is how we. Well, let's do the C before we get started. Let's just do the C anyways. Okay. So it'll be C squared equals A squared plus B squared. So C squared equals 4 plus 16 equals 20. So C is the square root of 20, which is what? 4.4 or something like that? Sorry? 4.4-ish? 4.5? Okay, let's say 4.5. Okay, so now let's sketch the hyperbola. The center is at 0, 0. The A is 2, so we should go 2 to the left and 2 to the right. Those would be our vertices. The C is approximately 4.5, so we're going to go 4.5 to the left and 4.5 to the right. Those would be our foci. And now we need to use the B. So, and this is the first time we've seen this. So B is 4. So if the A, here's the center, and A is from the center to the vertex, from the center to the vertex. B is the perpendicular distance, just like it was in an ellipse. You're going to go up 4 and down 4. And then dash line should be red. Now I'm going to make it blue. These 4 points, right, the vertices and then the points we just drew with by using B, are the midpoints of the sides of a rectangle. So you're gonna sketch in a rectangular box. That doesn't work. Let's go here. Didn't work. Can't see. Yeah, so sketch in a rectangular box. It's got those 4 points as the midpoints of the box, right? And then you're going to draw the diagonals of that box, right? The diagonals here like that. Okay. So let me write this in a different color. That's good. So the diagonals of that box are asymptotes for each branch of the hyperbola. Right? These are asymptotes. And we know what an asymptote is, right? It's a line on the graph that the function or the equation's graph is going to approach, but it's not going to touch. Right? So once you've drawn those in, then you're going to start at the vertex. We said it's horizontal. There's the vertex. We know the vertex, it opens up around that focus there, so we're going to draw in. There's my hyperbolas. There's my branches. Okay, so that's where the B comes in, right? B is just like it is in an ellipse. It's the distance in the perpendicular direction to the major axis or the transverse axis. But it helps us to draw a graph by giving us a rectangular box that we can draw diagonals, and those are the asymptotes. Now, if I had to come up with the equations for those asymptotes, remember that we went from the center to the vertex is A, right? And from the center to the top of that box, that was B. So what would be the slope of that line, this line right here, if you're going to go over A and up B? Rise over run would be B divided by A, right? M equals B over A. Right? And what about this line right here? Well, it's still the same dimensions, but because now it's got a negative slope, it'll be down B over A. So the slope is actually, I should have erased that, plus or minus B over A. So the equation would be, these two, if you wanted to just write them in one equation, would be y equals plus or minus B over A times X. What's the y-intercept of both of those lines? Because it goes through the center, and the center is the origin, the y-intercepts are 0. So these are the equations of the asymptotes. Now, those won't always be the equations of the asymptotes because it's not always centered at the origin. We'll have to make an adjustment for that one fact. Okay. So let's try another one. Okay, sketch the hyperbola. And in this case, they've given us the general equation, but it's not in the standard form, so we have to complete the square. And it works the same way. Other than, it's going to be a little different now because we're definitely going to have a minus in between those terms. So it leads to possibilities for messing up the sign of something in the second variable. So let's see, I'm going to get the x's together. 4x squared plus 8x minus 3y squared equals negative 16. Factor out a 4 from the x terms. 4 times x squared plus 2x space. And there is no y to the first term, so we don't have to worry about completing the square on y. So a little bit easier. What do I add here to complete the square? I got to add 1. I got all these numbers right. So if I add 1 here, then I got to add what to the other side? 4. So now I've got 4 times x plus 1 squared minus 3y squared equals negative 12. So what do I have to do to put it in standard form? Say again? I got to divide by negative 12. And you probably would have thought when you started this problem that it looked like it was going to be horizontal. But when I divide by negative 12, actually this term is going to end up being the negative term, and that's going to end up being the positive term. So it'll switch because of that, right? So divide by negative 12, divide by negative 12, divide by negative 12. So now this is the first term. I'm going to write it y squared divided by 4, right? That's what that is. Minus x plus 1 squared over 3 equals 1. Okay, is this one going to be horizontal or vertical? Because the first term is the y term, that's the positive term. The first positive term is y, therefore vertical. Okay, what is the center? Right? First, remember the h is always with the x, so it's negative 1, 0. Okay, let's see. What else do we need? We need the c. We could tell the a squared and b squared, but we're going to need the c, which will be what? C squared equals a squared plus b squared. Just a second, I'm going to check something. Okay, I did it right. Okay, so this is 4 plus 3 equals 7. So c is the square root of 7. What is that? 2.6? Okay, so now we can sketch in everything. The center is at negative 1, 0, which puts it negative 1, 0 right there. The a is 2 because this is a squared. So we're going to go up 2 and down 2. Right? We're going to go left the square root of 3 and right the square root of 3. What's the square root of 3? 1.7-ish, right? So that would put us about right there and there. Okay, what do we do with those 4 points? Make a box. Here's our box. Can't see that. There it is. That's pretty good. And then what do we do with that? Draw in the diagonals. And then what? Okay, that's all you need to sketch the graph. I mean, at this point, we know it's going to start at the vertex and it's going to approach the asymptotes. Because it's vertical, we need to sketch it in these two places right here. Okay, we still need to put the foci in there, and we need to come up with the equations for the asymptotes. So we know that the foci are up and down about 2.6. So this would be there and there. And if I did the coordinates, it'd be -1 plus or minus the square root of 7. Now, notice that if I'm going to do the equation, what are the slopes of these lines now? I mean, now because it's vertical, this is the distance that's A, and this is the distance that's B, right? It switches because it's vertical. A is the distance from the center to the vertex. That's vertical now. So this one is going to have a slope of positive A over B. That's going to have a slope of negative A over B. So if I was writing it, wish I had more room. Right, let me go one more. Right, if I was going to write this like we did on the last slide, right, we would say y equals plus or minus. Instead of saying B over A, we say A over B. And there's an X there. But now the center is not at the origin, so you're going to have to subtract the vertex. Right? In this case, it's -1, 0. So we would write it like x minus -1, and over here it's y minus 0, which is y, which is going to leave us like this. Y equals plus or minus A over B is 2 over the square root of 3. We would have to figure that out, times x plus 1. And if we had a y coordinate other than 0 there, then we'd have to subtract that, y minus k, and that would give us something to subtract, or something we would have to add to the other side. But the main thing to understand is, if it's a horizontal, your slope is b over a. If it's vertical, it's a over b. It changes that right there, which I believe will lead us to, when we're ready, right? These are the equations for the asymptotes in general, right? If it's horizontal, the slope is b over a. If it's vertical, it's a over b. And, if you see what this is, y equals k, I mean, you could think of it like y minus k equals plus or minus b over a x minus h. Right? Just wherever you have an x, subtract h. Wherever you got a y, subtract k. And now to solve for y, that k ends up being there. Okay. Okay, so find the standard form of the equation with these vertices and these asymptotes. Okay, so let's see. The vertices are at 3, 2, and 9, 2. So 3, 2, and 9, 2. That would be 6. That would be 9, 2. Okay, so at this point, we know the vertices, so we know is it horizontal or vertical, and we can find the center pretty easily, right? Is it horizontal or vertical? If the vertices are on this line, it's horizontal, right? And what would be the center? Right, this was 3, 2, and this was 9, 2, so it would be 6, 2, right? 6, 2. Okay, what is this distance right here? What does it represent to us? That's the A. What is the A? 3, right? A is 3. Okay, now, since it's horizontal, what do we expect this slope to represent? Is it B over A or A over B? Right, horizontal was B over A. So what that's telling us, our slope, right, these slopes right here, M equals plus or minus B over A. But we already know that the A is 3, right? So in this case, we could say plus or minus 2/3 equals, since the A is 3, what does B equal? Then B is 2, right? We don't have to graph these lines. We're just using them to find B. And then we can find, well, actually, they didn't even ask us to graph it or put foci on there or anything, so we don't even need the C. We just needed those two numbers, right? So this means B equals 2. Now, what if, because this is always it'll come up, if not in a homework problem, maybe it'll come up on a test. But what if you were looking at, these were 2/3, but this distance was 6, right? What if that was a 6? Then what would that tell you is the value of B? It would have to be 4, right? So understand that this is not necessarily the B and that's the A. That's a ratio. It's a ratio that the simplest form of it is 2/3. But you could have other values, right? Just take that into account, because it'll come up. It always does. So we know what our A is. We know what our B is. We know what the center is. That's all you need to write the equation, right? It's horizontal, so we need this one. X minus h squared over a squared minus y minus k squared over b squared equals 1. So we can just fill in 6, 2. So that's x minus 6 squared. I'm going to do this one at a time. Y minus 2 squared. The A is 3, so that's 9. The B is 2, so that's 4, equals 1. That's it. Right, they didn't ask us to graph it or anything. Just write the equation. Okay. Now, we saw the concept of eccentricity with hyperbolas, although they're not. I don't think they asked for it in the homework or anything. There's no example problems, but just to explain that we still calculate the eccentricity with E equals C over A, the same formula. So actually, I just copied that to just make the point. This is the same that we used for an ellipse. But what's changed? Right? With an ellipse, the C was always less than the A. So the values of eccentricity were always a decimal between 0 and 1. Okay, now they've reversed their position. Right? The C is always going to be bigger than A. So what kind of number are you going to get? You're going to get something where it's greater than 1. I mean, the very least it could approach 1, but that's it. So these are the two examples, right? If the eccentricity is large, that means the C, right? The C divided by A is a very big number, right? That divided by that is a big number. And you get something that's kind of flat. right? If the C over A is small, that means that those two are very close together. So when you divide this distance by this distance, you get a number that's closer to 1. And you see what does that make those look like? Right? Much skinnier than that. So that's eccentricity. Okay. So I don't even remember if they asked for eccentricity, but they do. You just do the same thing, C over A. Okay, then the last thing we're going to do here is this, again, this is what's called the general equation of the quadratic, right? It has terms. It has a place for a squared term, an x squared term, a y squared term, an x to the first term, a y to the first term, and a constant. And it's always equal to 0. Right? That's like the general form of this thing. Now, after we have a little bit of experience with circles, and we talked about this at the time. We have a pretty much experience now with parabolas, ellipses, and hyperbolas. If you're given the equation like this in the general form, you should be able to tell just by looking at it which shape is it that you're going to make out of that. For example, as we learned at the beginning, the circle has the A and C are equal. The coefficient of the x squared and coefficient of the y squared are equal. Now, the parabola is the only one of the 4 that only has one squared term. Right. Now, the way they say it here is just using the coefficients of x squared and y squared. If you only have one, that means the other one is 0. So when you multiply them, you get 0. Which leaves us with ellipse and hyperbola. Right? In the equations, what's the difference between ellipse and hyperbola? They have opposite signs, right? For the hyperbola, the squared terms have opposite signs. For the ellipse, they have the same sign. So if they have the same sign, then if you multiply A times C, whether it's positive times positive or negative times negative, it's going to be greater than 0. For a hyperbola, since they have opposite signs, a positive times a negative is less than 0. So if we look at these examples at the bottom, honestly, I don't use any of this A times C. Just, which one of these only has one squared term? D, okay, there's your parabola. Right. Which one of these has opposite signs on the squared terms? B, right? Positive and negative. So what shape is it? It's hyperbola, the one we just did, right? The two that are left, out of circle and ellipse, the circle has equal coefficients. So which one is it? Circle. And the other one, they have same sign, but not equal coefficients, ellipse. If you want to multiply A times C and do all that stuff, it's fine, but it shouldn't be that hard to just go through. You might take it in order, because if there's one shape that you're more confident, like pick all the ones in the list that have one squared term and write a P for parabola next to them, right? And then all the ones that have opposite signs, hyperbola, right? And just when you get it down to here, if they're equal, circle. Everything that's left, ellipse. Just a suggestion. Now, there is anything suspiciously missing from this list, from this general equation here? There's no B, right? There's no B. And if you have a B term, there is a B term in that equation, right? This is the real general equation of a parabola. AX squared plus BXY plus CY squared plus DX plus EY plus F equals 0. Right? If you have an XY term, then it's not going to be horizontal or vertical. It's going to be tilted. Right? Everything we've done up to now, it was straight horizontal or vertical. It was never at an angle. But if you have that term, then it's going to be tilted. And like I said at the beginning, we've dealt with hyperbolas before, right? We've dealt with this shape, y equals 1 over x, is an inverse variation, and it has a graph that looks like this. And those are the branches of a hyperbola, but they're not vertical, they're not horizontal, they're tilted like that. And, you know, what would happen if I multiplied both sides times x? There's my xy term. That's why it's a hyperbola that's tilted. In fact, it doesn't have an a squared or a c, or an a or a c. They're both 0, but it's got the xy. That's what makes it hyperbola. The next section in the book, which we're not going to cover, shows us how to graph something like that. And what you do is you actually calculate what is the angle that I would need to rotate the xy axis so that this shape would be horizontal or vertical with respect to the new axis, right? And that'll redefine x and y in a way that drops that xy term out of it. It's kind of neat. I mean, I never saw it before I had to teach pre-cal. But it's kind of neat the way that they do that. It's very computationally intensive and fraught with opportunity to make mistakes. So at this point, with limited time, we skip right over it. Okay. So that's it. Now I did cut a line out of here. There was a line, like there almost always is, about using hyperbolas to solve real-life problems. And there are some pretty good real-life problems which are involved with navigation. They're involved with placing yourself in an ocean, let's say, when you've got listening stations around, you're getting signals from distant listening stations. And based on the difference, again, because it's a definition of hyperbola, of when you get that message from the different stations whose locations you do know, it allows you to place yourself. And you know, when you're in a big, wide open ocean, that's kind of valuable. I know many of you have had Mr. Harrington before. He can tell you how in the Navy they use this stuff. That they probably weren't doing the level of stuff we were doing it here. They probably like looking up a lot of stuff in tables that were already prepared for them. But they were using this kind of math in navigation when he was in the Navy, and he learned that stuff. You could ask him about it. Okay, so these are the homework. These are just the matching, like we've had in the last couple. The last 8 are all the classify. So all you should be doing is writing down a letter. P, H, C, E. There's actually 16 problems there, but I just signed the first 8. Any questions? Nope.